It's just two of us.
Yeah.
I hope we're in the right place.
I do too.
Oh God. Are you in the lab?
No, I'm at home.
Okay. Drive. I don't know how, if I will be able to.
Sorry, what did you say?
I said I would try to drive. I really don't know if I'll be able to. Then if I don't, I would just park my car and then use the bus. So that's why I wanted you to help me, because I'm not sure of how long all that would take me.
Oh, yeah. I mean, like, I'll bring it over there and see if they'll let me put it up. So, for sure. Good luck.
You. I don't even know how it happened. Like, my shoes were wet. I was trying to go up the stairs. Then I'm like, oh, let me just go. Funny enough, like I was carrying my laptop. I put my laptop down. I was like, oh, let me go hang my jackets downstairs before going to my room. And next thing, I was down 3 steps.
Oh no.
3 steps. I went down. I'm like, oh my God, what is happening? I was on the floor for like 2-3 minutes because I couldn't get up. Then I dragged myself to my room and I was just there.
Oh no. So did you hurt your back or what did you hurt?
It's like the edge of the staircase, the right side of my waist kept on hitting all the edges. So I hurt my back.
Oh.
Like I have a bruise on my back and then my waist, like that was where all the pains was coming from.
Oh, that's awful. I'm so sorry.
It's fine. Thank you.
Hello, Hadassah. Hello, Haley. Let's see. Hello, Hanmant. Hello, Laura. How are things going for you, Laura?
Not bad. I would come for the poster presentation. Haley will help me take my poster. Yeah.
Okay, yeah. Haley, thank you for the help to Laura.
Yeah.
It's very friendly and professional. Let me check. Did the camera start it? No, I'm showing something wrong. Okay, yeah, this is better. So let me quickly make everyone a co-host so that you can Unmanned co-host, Umar co-host, Hadassah make co-host, yes. Heidi make co-host, yes. Lola make co-host, yes. So if anyone joins, please admit as soon as you notice it. Okay, so we are approaching the end of the course, and right now there is most interesting part related to the projects. And in the class material, there is a little reminder of the optical properties. So the goals of the class will be considered fulfilled if we, in the today and 2 lectures next week, if we cover what is necessary to run time-dependent density functional theory, so that we can add precisely computed optical spectra to the range of our theoretical tools. So, oh, hello, Amara. Nice seeing you connected. Let's compete. I was quicker to admit Rizvi. So the projects that you have selected are on this link. And when we meet tomorrow, ideally, there is a, so I want to give, to mention appreciation and support to those of you who have, who was thinking ahead and submitted jobs into the long queue of the NERSC. You see that some jobs are pending there for a day or two, and it is very reasonable if they are submitted before, and by the time of your arrival to the lab tomorrow, your main jobs, specifically molecular dynamics, will be done. So in a week from tomorrow, so let me go over this little slides. In a week from tomorrow, I'm inviting everyone to bring the tentatively the list, not list, the figures and captions for your written report, and during the lectures on coming Monday and Tuesday, I will provide instructions, provide suggestions what can be added to this. So basically, in a week and 1 day, we should have the first rough draft of the written report based on the course project. And so it will be some minimalistic example of a research paper. And figures and tables are major things. If there are no figures and tables, there is no reason to write other things. And then when they're ready, one can add on a little sections with like description of results, conclusions, introduction, things like that. And I will also, one of the homeworks was asking everyone to type in main equations of density functional theory. So later on, I will invite you to copy paste this equation that you typed as a methods section to this mini papers. So before you are contributing to your future. Okay. So, and I'm not showing the slides that we went over together. There are no common prescription, there is no universal prescription for research, but there are a couple of general motifs that can match at least majority of the researchers. So either to chop your model on 2 pieces, like donor and acceptor, substrate and adsorbate, and look if properties of single entity and combined entities match or these objects affect each other. And second motif, if you prepare a model, explore it at realistic or unrealistically high temperatures and see how the temperature treatment, how the change of geometry during molecular dynamics affects electronic properties at least and structural properties at most. And this is a good starting point if you do not have ideas what to do, but I'm sure you do. You may have much better ideas. There is another quick comment before we go forward. It is a little late, but still better late than too late. Please think on your background. Please practice sober thinking about geometry optimization. So in some situations, geometry optimization is not needed. For some projects, let me give an example. If you look how the geometry is changed due to thermal motion, the geometry will be corrupted. It will be ugly, especially if you heat the model to like 2000 to 3000 Kelvin. And after the end of this molecular dynamics, one does not need to re-optimize, because then it will come back to the ground state and you will see no signatures of the temperature. Or if I do not see Adam connected, but in his project, he is looking for how the promotion of a model to excited state changes geometry. So after such run, one does not need to re-optimize it back to ground state geometry. So in some cases, geometry optimization is not needed. There is a confuse because we use a template for in-car that tells in-car dash geometry dash optimization. So if one sets number of ionic steps NSW equals to 0, it means there is no geometry optimization. It's just single point calculation. Maybe in future years, I should fix it and make another template. So same in-car as for geometry optimization, but without ionic steps is just a single point. So it was one side. Another side, if you do big systems, if you are looking at sorbate of one molecule onto substrate, geometry optimization is needed. And there is another deception. So suppose I'm doing this VASP calculations for the first time. I think that I submit a job, relax, come back and get results. Sometimes this approach fails because the parameters for the job in the scheduler could be insufficient to treat your model. So if your model is big, you request, I want to do 1,000 steps of optimization. You give it only 30 minutes. It will not do 1,000 steps of optimization in 30 minutes. It may, for very big systems, it may not give even one step. So when it's to think creatively on a match between requests and resources. So just when job is going on, one can look into file OSI car and see how the steps of electronic and ionic optimization are developing. And the third comment, so it is a very basic thing that they are much more basic than projects that you are doing. It is often important that the requested amount of steps are finished before expiration of the wall time limit. It is important because if it hasn't happened, your VASP job may not save healthy wave car. And healthy wave car files with orbitals is critically needed for first spectra and second orbitals. So I just was browsing through a couple of the directories and noticed that it happened. So when submitted jobs, and it was stopped in the middle because of the wall time limitations, because system is big and wave car was not created. So watch it. If wave car is not created, maybe in the same or better in different directory, rerun the same job starting from the latest cont car, but do 0 ionic steps, NSW equals 0. And then for sure it will complete and write a healthy wave car. Okay, sorry for wasting your time for this little comments. That's, I just wanted to make them in case it may prevent us from any errors in the near future. Okay, so what are we going to do today, and where should we arrive? For several weeks, we all are practicing computation of absorption spectra, and I believe we were briefly discussing what are the equations behind these calculations, but the method that we are using in our projects with VASP are, right now we are using very quick but not sufficiently precise method. We use so-called independent orbitals approximations when the transitions are happening from one orbital to another one, which is very easy and comfortable for human thinking. But more precise, more reliable methods take substantial more time, and they use different concepts. One of the concepts that we are going to absorb within like today, next Monday, next Tuesday, that even a single transition, even a single line in a spectrum can be composed as superposition of many orbitals. So not if you are looking for HOMO to LUMO for lowest transition, it can be contributed by a mixture of both HOMO to LUMO plus one, HOMO minus one to LUMO, and they all contribute a little bit to the thing. And the transition energy is different, and oscillator strength is different. So main input of our efforts in less precise and more precise methods is the same. We input geometry and we get transitions and their oscillator strengths, energies and values of oscillator strength, and then compute spectra. But the mechanism, how these transitions are computed and what is behind them are quite different. And our last chapter focuses on this methods. From practical side, the simplest of the advanced methods, so-called TDDFT, is really nicely programmed in the Gaussian. And maybe during the lab or at least in the lecture, I will show input and output that give this reliable spectrum. This method, TDDFT, is also implemented in VASP. It is possible to run it there, but it will take longer time. I'm not sure if we have time to practice it for our big systems. And it is very closely by philosophy and by methods of implementation, it is very closely connected to so-called BSE, Bethe-Salpeter equation. So if your research life deals in the future with more and more precise spectra, it is a method that you're looking forward to study and practice. Okay, Phil, please stop me anytime for any questions, comments, and feedback. So last lecture, I think Tuesday, a week ago, we were speaking about the simpler than simplest, the lowest way to describe excited states, which deals with repopulation of the orbitals. In absence of such repopulation, the density is contributed by all orbitals up to the highest occupied, or one can replace this limit to infinity and then practice the occupation distribution function, which is selected as Fermi function at 0 temperature. It is completely occupied for all below equal HOMO and 0 equal above LUMO. And we went beyond this limit. We added 2 summations instead of 1 here, like over I and over J. And then instead of this F, we used density matrix IJ. Then we chopped the density matrix, which controls how pairs of orbitals contribute to total density, onto 4 segments. The segment or quadrant related to ground state, segment related to excited state, and then transition density. Now, when we are staying on the path towards TDDFT, time-dependent density functional theory, we want to admit the notation used by most practitioners of this theory. And they are using just X, uppercase X, sometimes as a vector, and uppercase Y for this segments of the density matrix. So let me check. Yep. So here are a couple of more slides that we were talking about last time. So this is not a derivation, it's just a conceptual symbolic representation. So in case a model is perturbed by electromagnetic radiation, which in the leading term contributed by dipole approximation. So the energy of interaction between light and matter is proportional to strength of electric field times dipole. So the segments of the density matrix, which determine overall density and can be inserted into feedback loop of DFT, are perturbed by electromagnetic field in different orders. So the segment corresponding to ground state is not, can be assumed as not perturbed, especially if the electric field is very weak. The transition density segments are perturbed as first order in terms of electric field or in terms of light to matter interaction. And the occupied rho EE excited density matrix is perturbed as a second power of the light to matter interaction. So if the light to matter interaction is small, like smaller than 1, then second power will be smaller than the first power of this interaction. Therefore, it is admitted approximation that this is neglected, this is considered unchanged, and therefore one needs to look only on the changes in the transition density matrix as function of frequency or period of the electromagnetic radiation. So it is a formulation of the what time-dependent density functional theory answers. So here is a little bit more of the notation that we may want to admit. I'm going to slowly explain what is shown on this slide, and then we will practice a little vote to make sure that everyone feels happy about this content. So let me focus you at, and I apologize that from lecture to lecture, color code of the segments may change. Let's focus on the center of this object first, so that we recognize something simple. So in the center, we have density matrix elements, each of which with 2 indices, and we do have ho-ho, lulu, holu, luho, right? You see it? So ho-ho is would correspond to occupation of the highest occupied molecular orbitals. Rho LU corresponds to occupation of lowest unoccupied, which may get occupied during photoexcitation, and transition elements rho LU, HO and rho HO, LU will be non-zero if a process of excitation is going on dynamically right now. So during the process of excitation, during the process of transition density matrix is non-zero. So transition, because it describes transition. Let me make intermediate vote. Is this concept, is the central 4 elements of this matrix look reasonable in their interpretation? Please just vote by thumbs up if you agree, thumbs down if you disagree. I think you had, okay, everyone, thank you. Now, a little notations and a little technical trick, which is only a trick. It doesn't have any philosophical deep scientific background, but without it, it would be hard to process further. Suppose we have many occupied orbitals and many unoccupied. Just to make our life simpler, I show only 2 occupied and 2 unoccupied. So highest occupied and highest occupied -1. Then we do have a segment rho GG. So it has both diagonal elements for occupation and transitions if there is something happening, if they redistribute transitions between these orbitals. Now, so it was in the red box. Now let me focus on the green highlighted box. So we do have lowest unoccupied +1, diagonal elements and off-diagonal elements that may change if we have some redistribution of occupations in the excited state. And both the non-highlighted red box and green highlighted boxes are not a focus of the TDDFT theory. The remaining 2 things, sky blue and yellow, correspond to all possible transitions between these 4 orbitals. So like from HOMO to LUMO, from HOMO -1 to LUMO, from HOMO -1 to LUMO +1, from HOMO to LUMO +1, and symmetric backwards. So excitation and de-excitation. We are looking, if we are followers of the TDDFT theory, we are interested only on this off-diagonal elements. And the values of each element of density matrix will be different depending on frequency of electromagnetic radiation. So the amplitude, the value, will be linearly proportional to strength of electric field. Therefore, we can skip it. Like transition density matrix will be linearly proportional. The bigger the field, the bigger the density matrix in certain limits. But depending on frequency, they will be changing dramatically because there will be resonance condition. If the frequency of electromagnetic field matches the transition energy of between orbitals or between excited states, then transition will go more vividly. So we are looking for response of the transition density matrix elements to the frequency, which is highlighted with this symbol omega, or sometimes we can use uppercase omega. So let's vote if this concept is okay. Yeah, thank you, Hadassah. Thank you, Hanman. Thank you, Lola. Thank you, Haley. Thank you, Amara. Thank you, Umar. Okay, let's go to the next little step. And here is the mathematical trick. So the scientific programming, applied math, and repository of pre-made programs made by humankind is tailored to solve very limited number of standardized problems. And there is a set of standardized problems that are needed for economics, for engineering, construction, for financial flows, for a lot of math, science, chemistry, physics, is problems of linear algebra. basically solving linear algebraic equations and finding eigenvalues of matrices. I believe you agree with this statement. Like main equation of quantum mechanics, Schrödinger time-independent Schrödinger equation, it can be reformulated in terms of finding eigenvalues and eigenvectors, right? And hello, Rizvi, thank you for rejoining. So a lot of scientific and non-scientific problems are reformulated as diagonalizing of matrices, finding eigenvalues, eigenvectors. And in this framework, just in order to utilize pre-made subroutines, which are optimized, which are made not only for computational chemistry, but for other computational problems, one can reset problems that we need to solve in terms that are most comfortable to process by pre-existing subroutines. So if we need to find the response of elements of transition density matrix onto the frequency, we may want to formulate our unknown object as a vector instead of matrix. So there is no deep philosophy or science in it. It's just a matter of comfort. Before, we were always talking about saving wave functions in the form of vectors and then finding eigenvectors by diagonalizing matrix of Hamiltonian, right? By finding eigenvalues and eigenvectors of the total energy matrix. Now we will search for a supermatrix by finding its eigenvectors. We are going to get the elements of the transition density matrix. It is not yet done, but we will set a problem in such way. So in order to pursue this question of numerical comfort, we are rewriting, we are reorganizing the way how the data for transition density matrix are stored. Instead of storing it in a form of a matrix with two indices, we are going to store it in a form of a vector with one super index, which includes both other indices. And here is this example. So we start with lowest and go to the highest. So transition from HOMO -1 to LUMO will be our first element. Then we go up, just follow the matrix. HOMO -1 to LUMO +1 will be the next one. Then we just follow rows in the matrix. Then transition HOMO to LUMO will be the next one. And the last one, the HOMO to LUMO +1 will be last one in this vector. And so one can put a little equation how to process these indices, but basically we just scan first row, then second row, then next row, and put all rows as a new big super column. So finding this vector is a numerical problem that time-dependent density functional theory wants to solve. Let's vote on this little statement. So if it is okay, please vote thumb up. If you disagree, thumb down. Okay. Rizvi, are you okay? If you do not like it, please speak and express concern. If you are speaking, I do. Oh, okay. I didn't check if you have good.
Yeah, it's okay. It's okay.
Oh, okay. Yeah. Thank you. Thank you. I hear you. Okay. And typical names for the subroutines are BLAS and LAPAC. If you do programming, you recognize them. Okay. So in the community of TDDFT, one talks about this ground to excited excitation transition density as X, the recombination transition density EG as Y, and then GG is assumed unperturbed, EE assumed negligible, and then one sets problem as finding uppercase X and uppercase Y as a function of omega. Okay. And basically, as an outcome of the theory, when we will go over it, we will get the list of frequencies at which this response will be maximal. And for each of these frequencies, there will be a list of transition densities, out of which we will need to compute oscillator strengths. Okay, so I am done not with the lecture, but with a summary of the goals of the TDDFT. We have a little bit more time, and instead of diving into this theory further, I want to provide several little pieces of like context knowledge, some background theories that are useful in getting overall idea of interaction between light and matter. So one can formally get through TDDFT theory without these things, but with them, it will be much easier. They create a general context. And I will just review a couple of contexts, concepts like Frank-Condon, Stokes shift, then completely irrelated to the lecture, but needed for the project, the one-dimensional charge transfer, remind transition dipole oscillator strengths, Einstein coefficient, and absorption spectrum. So we need to finish in like 20 minutes about here. If you got the meaning of the previous slide, you can relax. This, what I'm going to communicate is useful, but not critical. So consider it as entertainment. If you need it for your project, then concentrate. If you don't, then it is okay. So the concept of so-called Frank-Condon principle is critically needed for Adam. So Adam, if you're watching this recording, start focusing right now. Okay, and please raise your hands or thumbs if you have heard about this concept before, so that I feel a little more comfortable. No. Thank you, Hadath. Thank you, Hanmand. Amara?
No.
No, okay. Haley? Yes, okay, good. Lola? Yes, thank you. Umar? No. Said? Rizvi?
No.
Okay, so at least a couple. So if I fail to communicate it, ask Haley and Lola. So when we were starting this course, we spent noticeable time for speaking about the Frank-Condon, not Frank-Condon, Born-Oppenheimer separation, right? And in the concept of Born-Oppenheimer separation, we were telling that one can separately treat electronic states and potential energy surfaces as function of nuclear elongation, right? So there are several situations when both of these concepts come together and need to be treated at the same time. One of these concepts is spectra of small molecules. So if your molecule is not small, if you're dealing with like quantum dots or nanoparticles or carbon nanotubes, it is much less important. But if your molecule is small, and the criterion here is that the object has high frequency oscillations, then the revision of Born-Oppenheimer principles lead us to new features and new discoveries. So the image here shows the potential energy surface for the ground state, and for simplicity, it is plotted as a function of one coordinate. Everything can be redone for infinite number of coordinates. And there is an excited state. So if the potential energy surfaces are sharp enough, if they're not shallow, but sharp, the motion of nuclei in these potential energy surfaces, which often do not coincide, right? So potential energy surface for ground and excited state may look differently, may have different curvature and different equilibrium position. So for small molecules, nuclear motion cannot be considered classical. It is quantized, and it is symbolized by this eigenstates, which look like harmonic eigenstates: ground, first, second, excited, right? Ground, first, second, excited, and then transitions of the in this molecule from ground to excited induced by electromagnetic radiation happen not just from electronic to another electronic, but transitions happen between these vibronic substates. So one can change also quantum state of nuclear vibrations. And one should take into account mutual position of this equilibrium. So in the displayed image, most typical transition would happen from ground state mu0 to the excited state mu prime equals 2. And the frequency will be bigger than energy offset of this energies of electronic states in the equilibrium. Then in the excited state, there is a chance that system will relax to the ground state, ground vibrational state of the excited electronic state. And then the emission will happen from mu prime 0 to mu equals 2. So this thick red arrow. Because during optical transition, which happens very quick, the positions of ions do not change. The wave functions have less chances to change. So the Frank-Condon principle deals with introducing this feature into molecular spectroscopy. So if you want to speak about these features and compare them to experiments, one needs to have at least few parameters. One needs to compare the energies of excited and ground state for the geometry of the ground state. And then one needs to compare energies of excited and ground state for the geometry of the excited state. So to speak about these properties, we need 4 data points, 4 values of total energies. And based on these parameters, one can attempt to reproduce mutual position of these potential energy surfaces and reproduce spectra that one can observe on experiment. Okay. It is the same slide with just a little more notations. So overall wave function is composed of nuclear and electronic factors, and they change simultaneously in these things. So this little schematic drawing shows the absorption and emission spectrum. So typically the absorption spectrum, so here I showed two axes. Red axis shows, I'm directing into the opposite direction, so energy is bigger when we go from right to the left. So here is a big energy, here is small. So absorption transitions happen at higher energy than emission. And if you take the tallest peak in the absorption, tallest peak in the emission, their energy offset is called Stokes shift. For crystals, for very big molecules, for nanostructures, for solids, often the Stokes shift is small or negligible. But the smaller the molecule, the bigger the Stokes shift, and sometimes it is very noticeable, and it is experimental. It's possible to observe experimentally. This little image has two axes. Another axis is wavelengths, lambda, and it goes into the opposite direction. So on this language, on the language of the wavelengths, the emission has a larger wavelength than absorption, and one typically tells that emission is red shifted, because red is has longer wavelengths and smaller transition energy than blue. So emission is red shifted in compared to absorption. Although this was more entertainment than fundamental background, let's vote if these concepts are okay for everyone. Thank you. Thank you. Amara, Umar, Rizvi? Are you okay with? Okay, yeah, thank you. So here is an example of this Stokes shift for in a situation when it is not very big, for crystals doped by doping ions. It is small but still observed. Okay, another little concept is one-dimensional integration. So here the main client is again Adam. Adam, if you are watching, please focus on the slide. So it is an example that we were doing all together in the lab. So the object, which is labeled as 3D, is a molecule of two slightly different dyes, with metal and without metal. And green and blue are LUMO +1 and LUMO orbitals. So the analysis of three-dimensional orbitals sometimes is complicated, but if one is focusing on charge transfer, then one just needs to explore how things are changing along certain dimension. And if you integrate over X and Y and explore the distribution of charge density for orbitals along Z direction, we can say that like LUMO orbital is definitely attributed to this free base porphyrin, and LUMO +1 is attributed to this zinc porphyrin with this green color. And this data and images are much more compact, and one can immediately analyze the charge transfer. And sometimes for metal organic complexes, one can use the same analysis for identifying metal to ligand, ligand to metal charge transfer. So what we were doing in the lab last time is just integrating three-dimensional partial charge density over X and Y and getting it as a function of Z. There is another set of codes that we didn't practice that integrates over all three, multiplies by R and computes the dipole, static dipole, which is even better. So one condenses properties of three-dimensional orbitals just into one number, or into into one number. Three Cartesian projections. So if anyone needs it for the projects, I'll be happy to share, but if no one, then we'll just save time for other things. Okay. And one can use this analysis in publications really easily. Okay. Another little background concepts. We all are practically computing absorption spectra in the independent orbital approximation. We all are computing oscillator strength value. And I remember then at a time when you were presenting WASP skills, there was discussion on what is the meaning of last three columns in the oscillator strength file, right? I think it was resolved, but it's better to revise it once again. So although independent orbital approximations in TDDFT are different level of precision theories, their final answer, their final observable oscillator strengths and absorption spectra are the same. And the ways how this observable is computed are similar. So by revisiting the way what is oscillator strength and transition dipole, we help ourselves to get through the TDDFT theory. Okay, so the upper line in a box does show the symbol uppercase D vector sub with indices ij as a transition dipole between Kohn-Sham orbitals I and J. So by rules of quantum mechanics, one takes orbital I with conjugation, orbital J without conjugation, and one puts the operator of this observable in the middle. So operator of dipole is just charge times distance. So here is our charge, here is our distance. So by using two orbitals, position operator and making integration 3 times, one is getting a vector with 3 projections, and this vector will be different for each pair of orbitals, I and J. So let's vote if this notation makes sense. Yeah, thank you, Hadassah. Thank you, Hanmant. Yes, Rizvi? Okay, yeah, thank you. And do not hesitate if something is not clear. It's my duty to explain it. So basically, it is what our OS dipole version 3 is computing. So 3 Cartesian projections X, Y, and Z of the transition dipole, and it is what is written in the last 3 columns of the oscillator strength. If we need to compute only one projection, one instead of vector, one puts just projection here. Now, the oscillator strength tells whether the transition dipoles is a measure of ability of two pairs of orbitals to contribute to interaction between light and matter. So if transition dipole is big, then optical perturbation can promote electron from orbital I to orbital J. But if one needs the actual probability, then it will be proportional to the square of this transition element. Why square? It is not evident from this writing, but I'll try to briefly show it in a corner. So there is a Fermi's golden rule. Then the rate of a process is proportional to interaction energy squared times density of final states. The interaction between light and matter is proportional electric field times transition dipole. If we do V squared, it will be electric field squared and then transition dipole squared. Electric field, we can later cancel it because we need not the absolute value, but we need just a response. We need dependence on frequency rather than strength. So from this concept of the Fermi's golden rule, we need transition dipole squared. And if we like multiplying vectors, you can do it row by column, or it can be projection of x squared, projection of y squared, projection of z squared. So this transition dipole squared is the main contribution to the oscillator strength. Let's double check. I know I'm asking to vote too frequent, but let's vote that transition dipole squared is a good quantity to measure the transitions between orbitals. Just okay, yeah. So Hanmant has questions. Rizvi, are you okay? You okay? So if the initial and final orbitals are very far in space, right? Then such integral will be zero. So in order to be able to absorb light, initial and final orbitals should sit on the same molecule or on the same fragment of a molecule, right? And if they are far, there will be no absorption, no transition dipole. I think it makes a little more sense to it. Okay. And here is more precise equations that we are practicing for oscillator strength. That is, we use there. So major portion is for transition from orbital I to orbital J is transition dipole squared. And then there are factors that there are ways to derive them if one carefully processes it. So average over space, because dipole can be oriented in molecule can be oriented in any direction in space. There are elementary constants for like mass of electron, charge of electron, and one of the most important things is frequency. So this equation is used in what we do for computing oscillator strength, and then this Fij is used to build the spectrum. There are three types of optical activities: stimulated absorption, stimulated emission, and spontaneous emission. So this is a concept of Albert Einstein. So one of the several concepts he contributed to our civilization, and the diagram on the bottom shows two levels, right? So when we look for the absorption, it is a B12 coefficient. So we go from lower to higher level induced by electrical field. Then after the system is excited to is promoted to excited state, it can be de-excited to the ground state with the same intensity, B21. So B coefficients are very close, the B12 and 21. But in addition, if the system is promoted to the excited state and left alone, after some times, it will anyway release light. So we can excite molecules and keep it for a little time, and then it will spontaneously emit. The reason for spontaneous emission happens because there are zero oscillation of electromagnetic field of vacuum. So there is interaction with this zero oscillation of electromagnetic field. And the spontaneous emission typically happens slow, on the orders of few nanoseconds. And there is a connection between these coefficients. So all of them are related to the oscillator strengths. All of them are related to transition dipole squared. And the inverse of the spontaneous emission coefficient, so coefficient is a rate, right? And if one divides 1 over rate, it will be time. Right? So, and this time, 1 over rate of spontaneous emission, it will be lifetime. Lifetime. So basically, how long the excited state will live before it recombines back before it emits time. The lifetime of excited state is inversely proportional to the oscillator strength. By adding these other coefficients, one can get this important observable that one can also compare with experiment. And I believe in one of the versions of the os strength codes, it just prints one more column with this information. Okay, it's about time to finish soon. Einstein coefficients, I hope everyone is happy with them. So here is the absorption spectrum, how we compute it. So once again, we do summation. When we convert the list of oscillator strengths and list of transition energies, which are, I believe, column 3 and column 4 in the oscillator strengths. So we need to convert them into continuous distribution. So we make summation over pairs of orbitals and then multiply the intensity of absorption by resonance condition. So if the transition energy matches the resonance, matches the frequency of the exciting light, then we have additional peak in the spectrum. And we add a little sigma due to thermal line broadening to make it a little bit more realistic. So we replace the delta function by a little narrow Gaussian. Okay. So I think we are done with all concepts. So we will refocus on the theory of TDDFT next Monday. And I look forward to seeing you physically in the lab tomorrow evening. So meeting is done. Everyone welcome to disconnect. If there are questions, I'll stay here connected for a minute or two.
Thank you.
Thank you.
Hello, Dr. Dimitri, can you hear me?
Yes, Rizvi.
I have a question, but not regarding this lecture, regarding the project.
Okay.
The test file you have made, I have run it, and I plotted the DOS file. But I have a question of why the waveguide is of 0 KB file size in that.